Hello everyone. So I thought I'll record the solutions to a few quiz questions. So here it is. The question says the grouping structure shown in figure 1 is used to generate a carry. So this is figure 1. The dash is generated at the output of the cell at the fourth bit position. So fourth bit position is this. The total delay involved in obtaining the carry at the fourth bit position is dash. So let's see how to solve this. So basically, what does a gray cell do? So here, the gray cell takes the input P2, G2 and G1, right? And G1. So what will be the output at this position? Let me call this as X. So X will be equal to G22 plus P22 dot G11. Right? So what does this basically give you? This will give you a generate 2:1. So this is basically at the position X. So now let's see what we get at the position Y. So this is X. So let me call this position Y. So what do you basically get at position Y? Y takes in the input from 3. That is, it takes in the input G33 plus P33 dot, what is the next input? See, one input is this. One input is this, which is G33, P33. The next input is the X. So what is X basically? X is G21, right? So at the output Y, we are getting G of 3:1. Now let's take the next position, which is this. Let us take the next position, which is this. So let me call this as Z. Okay. So at Z, what are the inputs here? The inputs are G44, P44 and Y, which is nothing but G31. Therefore, I can write Z is equal to G44 plus P44 dot G3:1. So Z gives you nothing but G of 4:1. So now what is this? Basically, we need what is generated at this point, right? So as in what is generated at this point is what we are looking at. So let me call that as W. Okay. So I can write W is equal to, the input to this is Z, right? So therefore I can write W is equal to G of 4:1 plus P of 4:1 dot G of 0, right? This is generate 0. This is one output and this is the other, sorry, this is one input. This is the second input. So therefore W gives us what? G of 4:0. So the answer to the first blank is, it is G of 4:0 is generated at the output of the cell. And what is the total delay? So the total delay can be calculated as the delay for the calculation of the individual generate and propagate signals, that is bitwise generate and propagate signals. Let us call this as T of Pg plus, so what forms the critical path here basically? So it is this, right? So you have 4 AND ORs, right? You have 4 AND ORs basically. and then plus TPG. So therefore, the total delay involved in obtaining the carry at position 4 is nothing but you have TPG plus 4 AND ORs. So this is required to obtain G of 4 is to 0. And we do not need an XOR gate here, right? So because the question says the total delay involved in obtaining the carry at the fourth bit. So if you want to obtain the sum at this point, then you will have to add an XOR here. But then the question says carry at the fourth bit. So therefore you will not need T XOR. So this will be 4AO, the time taken for 4AO. So the next question is you have to compute the critical path delay from the delay diagram of 8-bit parallel adder shown in figure 2. So the 8-bit parallel output, the sum, that is S, the sum is obtained at this point. That is what basically forms the critical path is this, right? So you will generate and propagate signals through this, and then this basically forms the critical path. That's what the delay that you have to find here is what is the time taken to obtain this sum basically, right? So the question says bitwise PG has a delay of 1.5 bits. So this is basically the bitwise PG, right? So radix 2 PG has a delay of 2 nanoseconds. So radix 2 is for a gray cell that takes in 2 inputs. So these are radix 2 cells. All these are radix 2 cells, PG cells. So radix 3 PG cell has a delay of 3 nanoseconds. So here these are radix 3 PG cells, right? So this basically has both this generates both group generate and propagate signals. Radix 4 PG cells have 4 nanoseconds delay. As you can see, there are no radix 4 PG cells here. And the XOR gate has a delay of 1.5 nanoseconds. So this forms the XOR block. Okay, so now the delay of the bitwise PG is 1.5 nanoseconds. So now as you can see here, these three signals can be generated in parallel. That is these two black dots or black circles, that is radix 3 PG, as well as this first cell here. This first gray cell here can be executed in parallel. So that is basically this group can be executed in parallel, right? So now the delay of these two is given as 3 nanoseconds and the delay of this is given as 2 nanoseconds. So let's take the worst case, and all these three signals, that is at the outputs here, here as well as here, are obtained in 3 nanoseconds now. Let me say that this operation takes 3 nanoseconds worst case. Plus from here what forms the critical path? This forms the critical path. So it has 1, 2, 3, 4 AOs. That is 4 radix 2 PG cells. So each radix 2 PG cell has a delay of 2 nanoseconds. Therefore, 4 radix 2 PG cells will have a delay of 8 nanoseconds. Plus, the next delay is this due to the XOR gate. So this will be 1.5 nanoseconds again. So totally it will be 14 nanoseconds delay. So that is the delay that is required to get the sum at this point. If a designer wants to make NMOS 6 times stronger than PMOS, then what sizes the designer end up having for pseudo NMOS inverter logic? Assume unit size inverter has W by L of P is equal to 2 times W by L of N. So what does this basically mean is that if a unit size, this is a unit size inverter, right? So we have a static CMOS inverter, okay, where Vin is given here and then V out here. So if this has a size 1, then PMOS will have a size 2, which indirectly says that mu P is equal to half mu N, so that the charging and the discharging currents are the same, and let that be equal to I. So this charging, the discharging current, which is the current through the NMOS here, is proportional to mu N Cox W by L, and W by L is 1, and I charging is proportional to mu P Cox W by L. W by L is 2, but mu P is equal to half mu N. Therefore, this also I can write as ICH. I discharge and I charge of the unit inverter is proportional to mu N Cox. Right? So now we have to make the NMOS 6 times stronger than that of the PMOS, which means the current through the NMOS must be 6 times more, 6 times that of the current through the PMOS. So now let this be a pseudo NMOS inverter. This is Vin, this is ground, and this is V out. So since mu P is equal to half mu N, so if the size of this NMOS is X, W by L of this NMOS is X, then we have to make the W by L of this PMOS is equal to X by 3, so that the current through the NMOS is 6 times the current through the PMOS. This is because mu P is equal to half mu N. Of course, we have a capacitor here, right? So now what's the charging current? I can write I charging is equal to mu P, which is proportional to half mu N, which is nothing but mu P Cox, into W by L, which is X by 3. Therefore, I charging now in a pseudo NMOS is proportional to mu N Cox is the current through the unit inverter. This is equal to I, which is the current through the unit inverter. I can write this as X by 6 I. Similarly, I can write the current through the NMOS is equal to X times I. But notice here that the current through the NMOS is not actually the discharge current, because the current through the NMOS, okay, now is equal to the current from the PMOS, because PMOS is always on, plus the current from the capacitor here. So the current through this NMOS is equal to current through the PMOS plus this current, discharge current, right? Plus the discharge current plus I discharge. Therefore, I can write I discharge is equal to I NMOS minus I PMOS. So this is equal to X times I minus X by 6I, which is 5 by 6xi. This is the discharge current. So now what is the value of x that I should choose, so that I discharge current here is equal to the discharge current of the unit inverter. That is, this discharge current must be equal to the discharge current of the unit inverter. So what should be the value of x here? X must be equal to 6 by 5, which is nothing but the size of the NMOS, right? X by 3 is the size of the PMOS So this must be equal to 2 by 5. A ring oscillator is constructed from an odd number of inverting stages as shown in figure 3, which is this. If there are 29 stages and the inverter is constructed in a 65 nanometer process with tau, tau is nothing but the RC delay, calculate the frequency of the oscillation. So assume the inverters are unit sized with WP by WN is equal to 2:1. So first let's calculate what is the normalized delay of each inverter. So we can write delay is equal to P plus GH. So H is nothing but the fan out. So output of each inverter is connected to an input of another inverter. Therefore this is equal to 1. G is also equal to 1 because that is nothing but the input capacitance of the gate under consideration divided by the input capacitance of a unit inverter. So here it is 3 by 3, 3RC by 3RC, which is 1. Plus similarly the parasitic capacitance is also equal to 1. Therefore the normalized delay here is of each inverter is 2. And there are 29 such inverters. Now, for what forms one period basically? Let's try to analyze it with the help of 3 inverters here. Okay, initially let's say this is at 0, then this will be 1, then this will be 0, again this will be 1, and this one is given, this one here is given as the input to the inverter again. So therefore now this will be 1, 0, 1, and 0, and this forms one period, right? So therefore two times passing through these inverters, it forms one period. So therefore now there are 29 inverters, right? So if something passes through these inverters two times, then it forms one period. So T is equal to 2 times the delay through this, right? So now what's the delay through each inverter? It is 2 plus how many number of inverters are there? That's 29 inverters are there. So therefore the total time period is this. That's 4 times 29. So 4 times 29 is 160. So this is the normalized delay, that is 3. So now this has to be multiplied with the unit inverter delay, which is 3RC. Tau is given here. So multiplying this with the tau, that is the unit inverter delay, and taking the reciprocal of that gives the frequency of oscillation.